trash. I mean, so you look at the picture at the middle. So this is garbage just lying on the roadside or in a barren land, or you can even have a runoff produced by factories, runoff water. So look at the garbage water. So this is the water which is released from factories, the waste water which is being let out into the nearby lakes and rivers, which is a freshwater body. So you're contaminating the water. The water can't be used for drinking or even for the living beings or the fish or any other creatures which are living there. They're going to die because they can't take it. So pollutants damage the quality of air, water, and land. And can any one of you recognize the picture on the far left? That's a beautiful picture of the skyline of Shanghai, which is a commercial capital of China. So it's the commercial capital of China, Shanghai, Beijing, even New Delhi, Calcutta, Cairo, the capital of Egypt. So these are some of the most polluted cities on the planet. And there's a lot of garbage piled up on the roadsides or plus in the barren lands. Likewise, the air quality is so bad that it's not even recommended to go to these cities. So excuse me. So now let's see what exactly the definition is. The definition for environmental pollution is any undesirable change in the physical, chemical, or biological characteristics of any component of the environment, which includes either air, water, or soil, which can cause harmful effects on various forms of life or property. And these pollution is of various kinds. We're going to not talk about all these things in detail because we don't have ample time at our disposal, but I'm just going to mention that these are the various kinds of pollutions which exist, which we are contributing to. The first one being air pollution, the second one being water pollution, soil pollution, thermal pollution. What is thermal pollution? Thermal pollution, so let's say you have a factory, like a nuclear power plant. Nuclear power plant produces a lot of nuclear energy in the process of nuclear fission as well as nuclear fusion. In that process, a lot of heat gets generated. So in order for the heat to be controlled, so you want to make sure that the people living in the surroundings wouldn't get affected, you use those cooling towers. The cooling towers are the spiral towers which encircle the nuclear power plant. So what these do is that they take the hot the water which enters in, it's going to be pretty cold, but the water is going to absorb all the heat from the nuclear power plant, and then the hot water that comes out is going to be let out into the nearby lakes and rivers. So what's going to happen when the hot water gets let out into the nearby lakes and rivers? The fish and the other creatures which are living in there, they can't take the sudden change in the temperature, which is when they die. So that is called as thermal pollution, which we see quite often nowadays. So in order to prevent that from happening, we need to cool the water before we let it into these water bodies. And then noise pollution. I'm pretty sure you guys know what noise pollution is. When you go on a drive, you see a lot of cars, a lot of vehicles. They're honking at you like move, move. So that is noise pollution. A human ear can take about 85 decibels, not more than that. 85 decibels. If anything is more than 85 decibels, then it's considered to be extremely loud that our ear can't take. Okay, so that's noise pollution and marine pollution, followed by pollution due to the nuclear hazards. Yes, whenever there is a nuclear hazard, you're going to see a lot of nuclear fission as well as nuclear fusion reactions happening, and a lot of isotopes get generated, and that even kills a lot of people and causes a lot of deformities in the upcoming generations as well. And pollution due to natural disasters. The natural disasters which cause pollution include volcanoes. So you got even the hurricanes, the typhoons, the tornadoes, the flooding, natural forest fires. So these are all considered as the natural disasters. So there's going to be pollution that is caused by natural disasters as well. So let's concentrate more on air pollution because that is what my presentation focuses more on. So causes for air pollution, there are natural air pollutants as well as the anthropogenic, which is the man-created pollutants. Natural air pollutants come from, as I mentioned to you in the earlier slide, come from volcanoes and earthquakes and other events. But anthropogenic pollutants, as you see in the picture, they come from industries, they come from factories, they come from the chimneys, or whatever you call them, and they come from even the vehicles which we drive, the exhaust pump of the vehicles. They produce a lot of poisonous gases which are released into the air, and which is released into the air, into the atmosphere. And these are called as anthropogenic pollutants. The chemical compounds that lower the air quality are usually called as air pollutants. And these compounds are of two major kinds. They can be either in the gaseous form or in the solid particulate form, which are suspended in air. You might have seen certain cities like New Delhi. New Delhi has a lot of particulate matter. So when you see New Delhi, when you jump out of the house in New Delhi, you see a lot of particulate matter floating in air. And that is what a solid form. So we're not talking about the gaseous. So we've got two forms, the gaseous form and the solid form, which is extremely fine particulate material, which can get embedded into your lungs. And sometimes even the lungs would stop functioning because the lungs get calcified. You know, they become hardened, so they don't contract and expand. That's what happens when you inhale these solid particulate materials. I hope. So let's concentrate more on the gaseous air pollutants. So oxides of carbon are the ones which we will be more focusing on. So gaseous air pollutants comprise of oxides of carbon, which include carbon monoxide as well as carbon dioxide. And they include even oxides of sulfur, like sulfur dioxide. It becomes sulfur trioxide, which upon dissolving with water becomes sulfuric acid, which comes down in the form of acid rains. I'm pretty sure you've heard of acid rains. So when there's a lot of pollutants in the air, whenever it rains, the rainwater washes or reacts with these gases which are present in air, thereby bringing down the so-called acid rains. And same is the case with oxides of nitrogen, nitrogen dioxide, which look at the structure of it. It has its resonance form. So nitrogen dioxide reacts with water to form nitric acid, and that even comes down in the form of an acid rain. And apart from these oxides of nitrogen, carbon, and sulfur, there are other volatile organic compounds like methane, which is released into the atmosphere. Methane is one of those compounds which can be used as fuel. As a matter of fact, in the United States, methane is used as a cooking gas. In India, I think we use a cylinders, which is butane, isobutane is what we call them as the LPG or liquid petroleum gas or whatever you call it. But in the United States, there's a common pipeline where they use methane, which is used for cooking. So volatile organic compounds even get released into air, and likewise there are chlorofluorocarbons. So lots of chlorofluorocarbons which get released into air. We're not going to talk about all these things, but these destroy the ozone layer. So these chlorofluorocarbons have the capability to react with ozone, thereby depleting the ozone layer and causing the formation of the so-called ozone holes. So the chlorofluorocarbons of many kinds, for example, the chlorodifluoromethane. So methane having one chlorine and two fluorines, which is chlorodifluoromethane, and 2-bromo-2-chloro, 1,1,1 trifluoroethane, the structure of which you see on the top right-hand side of this slide. And apart from these, you even see ammonia being released into air as one of the gaseous air pollutants. I don't know why. Okay, so out of these, as I mentioned to you, we're going to be focusing more on the oxides of carbon, which include carbon monoxide and carbon dioxide. Carbon monoxide, so I'm pretty sure you guys did come across carbon dioxide at some point. A carbon monoxide is a colorless, odorless, tasteless, and a toxic air pollutant. It is produced by the incomplete combustion I've underlined it and even put it in italics as well as in bold because it is caused by incomplete combustion. What is combustion? Combustion is burning of something in the presence of excess oxygen. So for example, look at the picture at the bottom of the slide. So you got a hydrocarbon, which is burning in the presence of oxygen, which gives two compounds, which is carbon dioxide and water. And of course, it gives energy as well. So in this process of combustion, when the combustion process is incomplete, I made it clear, when the combustion process is incomplete, and that is when you see the release of carbon monoxide. But when the combustion process is complete is when you see the formation of carbon dioxide, which we're going to talk about in the upcoming slides. So carbon monoxide is produced in the incomplete combustion of carbon-containing fuels such as gasoline, which is petrol, natural gas. Sometimes we use natural gas in the car. Some of the cars run on natural gas cylinders. Oil, coal, wood, and all these things. So these things, when they burn in the presence of oxygen, partial presence of oxygen. So when they're not for example, so let's say you're burning wood in a house. So in the house, there is not enough of oxygen in there. So for that reason, the wood doesn't get completely burnt. So that is when it undergoes the so-called partial combustion or incomplete combustion, which is when you see the release of carbon monoxide. I'm going to talk about some examples about the carbon monoxide poisoning in the upcoming slides. Just keep an eye on it. So the largest anthropogenic source of carbon monoxide in the world is vehicle emissions. Yes, whatever the gases which are released from the vehicles, they produce a larger amount of carbon monoxide in them. And breathing the high concentrations of carbon monoxide typical of a polluted environment leads to the reduced oxygen transport by hemoglobin and has health effects. So I'm going to briefly explain this to you in the upcoming slide. So this is exactly what happens when oxygen, when we breathe in air. When we breathe in air, what happens? The oxygen which is present in air gets absorbed by the hemoglobin, which is a protein. Okay, so oxygen from the pulmonary alveolus, which means the oxygen from the arteries of the lungs, get absorbed by the hemoglobin, which is the red blood corpuscles, and the oxygen then binds. So oxygen is the blue colors droplet kind of a things. So that's oxygen which is binding onto hemoglobin to form the so-called oxyhemoglobin. And this oxyhemoglobin, which is oxygen bound to hemoglobin, forms the goes to various parts of the body. So hemoglobin in the blood carries oxygen from the lungs to the various parts of the body, and that is when it supplies. So what happens then? The bond between oxygen and the red blood cells, it breaks, thereby releasing oxygen to the respective tissues, and that red blood cell, it absorbs the carbon dioxide from the tissues and thereby and then takes it back into the lungs, and that is when we exhale. So when we exhale, what comes out of our body is carbon dioxide, which is collected by the RBC at the various tissues. Okay, so this is what happens in a regular respiration cycle. It is a cyclic process. Now, what happens if instead of oxygen, you supply carbon monoxide? So when you inhale carbon monoxide, just like oxygen, it comes and binds to hemoglobin, the hemoglobin which is present on the RBC, to form carboxy hemoglobin. Okay, so carboxy hemoglobin. So as we've seen earlier, the oxygen hemoglobin bond first forms and then it breaks later on. But once, in case of carbon monoxide, once the carbon monoxide oxygen the hemoglobin bond forms, which is once the carboxy hemoglobin forms, there is no more of bond breakage seen because it forms a very strong bond. Okay, so that's the reason why. So when you inhale carbon monoxide, I'm going to show you some examples in the upcoming slides. So when you inhale some carbon monoxide, it's not like lethal drug for you. It's gonna be initially you're gonna get some headache and all that stuff. So as I said to you earlier here, so you'll be initially getting headaches because there's going to be a decreased supply of oxygen to your body. So when there's a decreased supply of oxygen to your body, what happens? You're going to start getting headaches. You're going to start getting increased risk of chest pain for persons with heart diseases and impaired reaction timing. Okay, so your body even it doesn't start working properly because you're not getting enough of oxygen because the hemoglobin is bonding with carbon monoxide to form carboxy hemoglobin. And if you keep inhaling this carbon monoxide, let's say for all day or all night, what happens is that the entire hemoglobin, which is present in all the red blood corpuscles in your body, they get saturated with carbon monoxide, and all what you see is carboxy hemoglobin, and that is when your body can't take, your blood cells can't take any more of the oxygen, and that is when you die, because when you can't inhale any oxygen and your blood cells are super saturated with a lot of with the carboxy hemoglobin, so which forms a stable compound, so you can't inhale any more oxygen, and that results in death of the people. So carbon monoxide not only affects the health of the people, it even affects the climate to a certain extent. Locations that continue to have a higher concentration of carbon monoxide tend to have topographical or meteorological characteristics that exacerbate the pollution. For example, check this out: strong temperature inversions or the existence of nearby hills that inhibit wind flow may limit pollutant dispersion. Okay, so in places where there is excessive amount of carbon monoxide, you would certainly see some climatic changes. So this is how it works. So carbon monoxide binds to hemoglobin, then that's it. It forms a stable bond, and it has, as a matter of fact, carbon monoxide has a greater affinity to bind to hemoglobin, which is present on the red blood cells, in comparison to oxygen. So once it binds, that's it. It's not going to break any further, and your hemoglobin forms the carboxy hemoglobin, which is of no use to your body. And here are some of the examples in newspapers. So check this out. In the Hindu, they put a thingy on in Karnataka. Four youths found dead in a suspected case of carbon monoxide poisoning. Why? So I was reading this entire article. The guys were of the age of 18 to 20. So people were suspecting, or something happened. Someone poisoned their food. Something, so maybe they killed themselves. But later on, they came to know that they turned on the generator within the house. They closed all the windows. They turned on the generator because there was no power in the house. And the generator, when there was not enough oxygen in there, what happens? There is partial combustion, as you have seen earlier. I mentioned to you here, incomplete or partial combustion, which released carbon monoxide. So it released carbon monoxide in excess in that room. Everyone inhaled it, and they inhaled it until there is no more of the hemoglobin that is left behind to bind to carbon monoxide, and that is the reason why all four of them have died. A similar case has happened in Mangalore as well. Three guards die at a bank in Mangalore from carbon monoxide poisoning because, when it gets cold during nighttime, what they do is they go to a room, they close all the windows and doors, and they light fire. They gather chunks of wood and they light fire. So what happens? So when they close all the doors, there's not enough of oxygen in there, which means that there's going to be partial combustion of the wood that they are burning, and that is what they inhaled, and all the three guards died, which later on people came to know. Initially, they suspected that maybe the robbers, or the burglars, they killed them or something happened, but they got killed because of carbon monoxide poisoning. Now, let's come to the it topic, which is the carbon dioxide, which is what our entire presentation is dependent upon. What exactly is carbon dioxide? So it is a colorless gas having a faint, sharp odor and a sour taste. It has a sour taste, not that I'm asking you to taste it, but it has a sour taste. It is one of the most important greenhouse gases linked to global warming, but it is a minor component of the Earth's atmosphere. As HO is only about, I'm sorry, I said it's 4.5 ppm, but it's 412 parts per million, which is about 0.0412% of the entire air that we are surrounded by. That's 0.04%. Okay, 0.04, which is negligible. So you might be thinking, oh, this is such a small amount. Why is this carbon dioxide affecting the atmosphere, the greenhouse, to a greater extent? So we'll check it out, why it is doing that. Though it is an extremely small component, a small concentration, it is playing a significant role in global warming. So it formed by complete combustion. As I mentioned to you earlier, in case of carbon monoxide, it is formed by partial combustion or incomplete combustion of various materials like wood, fuel, or whatever it is. But in case of carbon dioxide, it is formed by complete combustion of carbon-containing materials, as well as in fermentation. So in fermentation, so let's say like you ferment some, I mean, I do this fermentation at home. So I take a lot of vegetables and I soak them in some salt water and some spices and stuff. That's called fermentation. In that process, there is the carbon dioxide that is getting released, and that is called as fermentation. And even in respiration of animals, including us human beings, like look at the lungs over there on the far right, they clearly explain to you that carbon dioxide is eliminated out when we exhale, and when we inhale, it's the oxygen that is binding to the RBCs, which are present in the body. So the presence of gas in the atmosphere keeps some of the radiant energy received by the Earth from being returned to space, thus producing the so-called greenhouse effect. So yes, I've heard of greenhouse effect. I'm pretty sure everyone heard of greenhouse effect, but greenhouse effect. So this is what greenhouse effect is. So this is Earth, planet Earth. I'm pretty sure you guys can recognize it. This is planet Earth, and you've got a thick layer of atmosphere, which is comprised of various layers like troposphere, which is the closest to the planet Earth, followed by stratosphere, mesosphere, and thermosphere. So all these are the various layers of the atmosphere. So what happens usually is when sun's rays fall on Earth, they should get reflected. Okay, so they should get reflected back outside, or they should fall on the Earth's surface, and they should get reflected. So in that process, what is happening is that there is no heat transfer from the sun to the Earth. But what is happening when CO2, when you have a lot of CO2 in air? CO2 and other gases in the atmosphere trap heat, keeping the Earth warm. So CO2, it forms a thin layer in the atmosphere. So some sunlight, so what happens, some of the sunlight gets reflected backwards, but some of the sunlight undergoes this internal reflections. Check this out. The gases which are present over here, the pale yellow thingy which you see, I hope you guys can see my cursor. So the gases, or the gases which are present in the atmosphere, they prevent the reflected light to leave the atmosphere. So the reflected light reflects within the atmosphere, thereby increasing the temperature of the Earth. And that is called as greenhouse effect. So what is happening in this process? It is increasing the temperature of the Earth. So when the temperature of the planet increases, what happens? All the icebergs and the glaciers, which are present in the Arctic and the Antarctic regions, they melt. What happens when they melt? All the ice becomes all the snow or the ice becomes water and the sea levels increase. As when the sea levels increase, what happens? All the low-lying areas or the coastal areas get submerged. I can talk to you about a lot of examples within India. There are a lot of places like southern India. I visited a place called as Mahabalipuram in Tamil Nadu, which has got submerged in water. I'm not sure whether it is because of global warming or for some other reason, but it's some of it is submerged. Likewise, in Gujarat, we got Dwarka. Dwarka, the entire city, the entire town is submerged in the Arabian Sea. So there are a lot of examples we can come up with within India as well as in other countries. And as a matter of fact, you might be wondering, are there any places outside in the planet, outside in Earth, which are getting submerged? As a matter of fact, there's one city called Bangkok, capital of Thailand. It's the first capital that is going to get submerged if the temperature, if the concentration of CO2 goes up from 0.04% to 0.05%. This is the first capital city on the planet, which is Bangkok, which is going to get submerged, which is going to go underwater because it is a coastal city. Look at this. This is where the Bangkok is. This is a map of Bangkok, Thailand altogether. And the red areas that you see here are the areas which are prone to get submerged in water. And Bangkok is a a port city. And yes, it is at the verge of getting submerged in water. Now, going back to this thing, industrially, so carbon dioxide, so industrially, carbon dioxide is recovered from numerous diverse applications from flue gases. A flue gas is whatever the gas that comes out of the flue. So when you have a factory, so you got the big chimney kind of a thing, right? And those are called as flue. And the gas that comes out of the flue is called as a flue gas, which comprises of everything: oxides of sulfur, nitrogen, or carbon, and all kinds of stuff, ammonia as well. Industrially, it is recovered for numerous CO2 is recovered for numerous diverse applications from flue gases as a byproduct for the preparation of hydrogen, for synthesis of ammonia, from lime kilns, and from other sources. So we're going to talk about these applications of CO2 in the upcoming slides, but let's move on. So you might have all heard of carbon cycle. So why is all this happening? Why are cities or the lower or the coastal areas getting submerged in water? So you might have all heard of this carbon cycle where you see like the sun produces the solar energy, which gets absorbed by the plants. Plants undergo the so-called photosynthesis, excuse me. Plants undergo the so-called photosynthesis. I'm sorry, I'm gonna maximize the screen in a second. Through photosynthesis, and the animals eat the plants, and animals even breathe. In that process, the carbon dioxide is going into the atmosphere, and animals and plants, when they die, what happens? They decay and they produce carbon dioxide, as well as, of course, if they are underground, they end up producing fossil fuels. And you can even burn the fuel, and that is when the poisonous gases are released into the atmosphere, and some of the carbon dioxide goes back into the atmosphere. This is like a cyclic process. But look at this. In this cyclic process, this is called as a carbon cycle. This is a biogeochemical cycle. It's just like the phosphorus cycle, sulfur cycle, nitrogen cycle. So carbon cycle is unique. So in case of carbon cycle, the cycle has an offset. As you see here, the cycle has a branch, which is not a part of the cycle, which is obtained because of burning of fossil fuels. Okay, so the fossil fuels which are obtained, because it takes millions and millions of years for the fossil fuels to be formed. It doesn't happen overnight. So the fossil fuels, when they burn, they produce these poisonous gases like CO2 and other gases. They get released into the air, into the atmosphere. So now there's going to be a slight imbalance in the carbon cycle, because the carbon dioxide which is being absorbed is not being that's absorbed. So there is going to be a small imbalance, and that is the reason why there is a slight deviation in carbon cycle, and that's the reason why you see pollution. And when you look at the pollution, the pollution of the pollution because of carbon dioxide obtained from fossil fuels from various countries, you see India is at the bottommost, which means I'm pretty sure you guys know that India is a developing country compared to the United States and Europe. Europe and the United States are developed countries. They're more developed countries. The more developed countries, as a matter of fact, they always complain to us saying that we are the ones who are creating garbage. We're the ones who are polluting the environment, but they are the ones who are creating more damage compared to what we are, because they are the developed cities. I'm not telling you my opinion. I'm telling you a fact. This is a fact. The developed cities, the developed countries are the ones which are contributing to a greater extent for environmental pollution. And India, as it's still a developing country, it is at the lower level. So we're not contributing to that great extent. Doesn't mean that we can go ahead and start burning everything that we see. Now, we do have to make sure that we have a control in whatever we are doing. So now, what are the ways to curb carbon dioxide emissions? How can we control all these things happening? So we've seen the carbon cycle, wherein we see carbon dioxide, which is produced from the factories and the vehicles and other places. So how can we control the increase? How can we control the release of carbon dioxide into air? How can we bring down, how can we reverse the global greenhouse the effect? How can we reverse it? So the aim of Mission 2020, so all the countries have sat together and they came up with the so-called Mission 2020 on pollution, which is to bring a new urgency to the global climate conversion. It is imperative, it's extremely important to make sure that we absorb a lot of carbon dioxide which is present in air, because even though it's a very small amount, it is causing a greater destruction to the planet, with a call to begin rapidly declining global greenhouse emissions. So in this particular Mission 2020, there are a lot of things which they came up with. First thing is energy. They made it clear that we all have to start using renewable energy resources. Okay, we need to start using renewable energy resources. There are a lot of renewable energy resources out there. So we can start using solar energy, we can start using wind energy, we can start having windmills. And as a matter of fact, at GITAM, where I'm working at, we have solar panels on the top, because they do supply electricity for part of the campus. So we are going the renewable part. So likewise, when it comes to infrastructure, we have to opt for greener buildings. Like look at, for example, the building on the bottom right. The building, it's called as a green building because it has large glasses. Large glasses are meant for getting more lighting during daytime. I'm sorry, not during nighttime, but during daytime you get more light from sunshine, and that is when you don't have to turn the lights on. And apart from that, you need to have more open spaces. You need to even have more space, more room for growing plants and trees. Okay, that is what is called as green building. And there are certain buildings, as a matter of fact, some of our historians have constructed some of the buildings where which are very cold, even it is hot outside. So it is the architecture of the building that reflects what it is like on the inside. So that is what is called as green building technique. And then transportation. So there are a lot of excuse me for a moment. There are a lot of hybrid cars which are present in the market, like the Toyota Prius, Maruti, and you even have the MG Hector, which is the British company. They're doing a commendable job in producing electric cars, or as well as the hybrid vehicles. Some of the cars which I have seen, they work, they're called as hybrid cars. They work on petrol or diesel. They even have solar panels on them, and they even have a battery operator. So you can go to a nearby station, battery charging station, and charge your car, and boom, you're good to go. So likewise, the fourth important thing, and which was come up in Mission 2020, is land, which is in order to minimize deforestation, in order to minimize mining, because when you mine, what happens? You're removing the top fertile layers. So let's say one of you have come up, said that, okay, there is a big mine of coal near my house. So what you do, you just go and dig the top layer, you make a big hole and you start digging out the coal. So what is happening in this process? The top fertile layer of soil is getting removed. And in that process, for that to happen, you even are doing a lot of deforestation, removing a lot of forests in order to get to that point of mining. So that's something which needs to be protected. So deforestation, mining should be minimized. That's one of the main missions of main goals of Mission 2020. And industries should cut emissions to half by 2050. What they're going to be doing? So there are ways in which the industries can cut emissions, which we will be talking about in the upcoming slides. So they can use something called as a scrubbers. The scrubbers are the ones which they're going to be putting in the chimneys of the factories. They can absorb certain gases before, and only the good gases can be let out into the atmosphere. Likewise, finance, there's something called as a green bond. So what exactly are these green bonds? So this Mission 2020 has made it clear that they have to come up with at least $1 trillion, 1 trillion, TRILLION, $1 trillion of money for green bonds. So what exactly are green bonds? They're created to fund projects that have positive environmental as well as climate benefits. So these are the projects which are developed by various governments to come up with better positive environmental as well as climate benefits. So now we talked about how we can curb carbon dioxide emissions. Now, so let's say we already have, I already mentioned to you, we already have about 417 parts per million, or 0.0417% of carbon dioxide present in the air that we are breathing. How can we bring that concentration down? So that is called as sequestration. So now is when we just entered into the main topic of today's presentation, carbon sequestration. So what exactly is carbon sequestration? It is a process of capturing and storing atmospheric carbon dioxide. So you're capturing carbon dioxide and you're storing it and you're utilizing it for various purposes. We're going to look at all those purposes in upcoming slides. Nothing to worry about. It is a method of reducing the amount of carbon dioxide which is present in the atmosphere with the goal, with the intention, the prime intention of reversing the global warming. So you're making sure that the concentration of carbon dioxide in air, which was 0.028% in air before the industrial revolution had begun. It went up to 0.0417 right now. So the main goal right now is to bring that concentration of CO2 back to what it was before we ruined the planet, before the industrial revolution. And there are three main ways. There are three different ways of carbon sequestration, carbon dioxide sequestration. The first one is chemical methods, and then we have the biological methods, and then the physical methods. So let's jump into chemical methods and see what kind of reactions we can carry out and what kind of ways in which we can absorb that atmospheric carbon dioxide and make and store it in different forms which can be stable for centuries to come. So the first chemical method is mineral sequestration, or simply called as mineral carbonation. So what you're doing is that minerals are absorbing carbon dioxide, hence you call it as mineral sequestration, or it is also called as mineral carbonation because the main reaction that is happening is that you are converting a metal oxide into a carbonate. Hence it is called as the mineral carbonation. So it's a fixation of CO2, which is carbon dioxide in the form of inorganic carbonate. So let's consider MO as a metal oxide. M is a metal oxide, reacts with CO2 to form a metal carbonate by releasing plenty of heat. Okay, so the examples include most of the oxides which are used in this process are oxides of calcium and magnesium. So calcium oxide reacts with calcium carbonate, carbon dioxide to give calcium carbonate. Likewise, magnesium oxide reacts with CO2 to form magnesium carbonate. Okay, so as a matter of fact, I'm pretty sure you guys never heard of this. 1 ton of carbon dioxide can be absorbed by 1.6 to 3.7 tons of rock on the planet, which clearly implies that the entire carbon dioxide in excess on the planet can be absorbed by the rocks which we have in the Earth's crust if proper initiatives are taken. And there are a lot of other oxides of metals which are seen, which I've shown you here. The first one is olivine, which is a magnesium silicate, which reacts with carbon dioxide to form magnesium carbonate. Silica, which is just sand, and it releases energy. Likewise, you have serpentine, which is a salt of magnesium and silicon, which is oxide of magnesium silicon, and it reacts with carbon dioxide to form magnesium carbonate, silica, as well as water. Likewise, you have wollastonite, which is a calcium silicate, reacts with carbon dioxide to form calcium carbonate, silica, and releasing of energy. So this is the process in which it happens. So the carbon dioxide which is generated in the power plants as well as the industries, they are sent to the mineral carbonation plant. As I mentioned to you, this is a process. This process is called as a mineral carbonation. So all these garbage or the CO2 which is generated in the industries and the power plants is sent to the nearby mineral carbonation plant, which is where the feedstock. You look at this, the table on the top right hand side. You use the feedstock, which is wollastonite, olivine, serpentine, the ones which we have seen in the earlier slide. We use these as a feedstock. So what happens is in the mineral carbonation plant at certain temperatures, this carbon dioxide reacts with these metallic oxides to form the respective carbonates. The respective carbonates can either be used in construction, which we're going to talk about in the upcoming slides, or either it can be discarded, or it can be it can be stored, or it can be reused. Okay, so these are the various ways of comparison of different carbonation routes. Carbonation can be done either by gas solid method or aqueous method, or by using hydrochloric acid extraction, or by nitric acid extraction, or using a molten salt or ammonia extraction. They all have their own advantages as well as disadvantages. Like for the first one, gas solid method is a sluggish reaction. It happens extremely slow, so it is not really a preferred one. And in case of the aqueous reactions as well as reactions with hydrochloric acid and ammonia, they tend to be extremely pricey. They are expensive. They are pricey reactions. So it's not a good idea to go for these unless you have no other way to do it. And there are other reactions like other conditions like using nitric acid extraction, where the products which are used are not recovered. They're non-recovery of the chemicals, which means all the compounds, all the reactants which you use, they get consumed in the reaction, which is not really something that's favored. And in case of molten salt, it is extremely corrosive, and you end up seeing a lot of unwanted byproducts. Okay, and the second way of chemical method is by electrochemical sequestration of carbon dioxide. I found a beautiful article in Nature Communication where it clearly says that at room temperature, carbon dioxide reduction to solid carbon. So what they're doing is that they're taking carbon dioxide gas and converting it into carbon, which is the black thingy, the black substance. So at room temperature, CO2 reduction to solid carbon species in the presence of a catalyst, which is cerium based. So let's see what exactly they have done in this beautiful paper in Nature Communication. So they started with a cerium it says Galenston. Galenston, which is the cerium obtained from an ore called Galenston. Galenston gallium it's a mixture of gallium, indium, and stannum, which is tin. So that is first made to react with oxygen to form cerium oxide. Cerium oxide then is made to react with water to produce cerium zero, and that cerium zero is made to react with carbon dioxide to produce cerium oxide, and this is where you get your elemental carbon. And look at this. So this, the black substance that you see in the tiny little vial, that's the carbon which has formed in this reaction by making this reaction cerium catalyze it. Okay, cerium is catalyzing the reaction. What it's doing is that it's converting itself into the oxide, and that oxide and by releasing carbon in its elemental form. So you might be wondering, so how can we just get carbon dioxide filtered out from the air? So these are the huge fans which are used in certain companies. What they do is these fans spin at extremely high speed. Look at the comparison of the size. Look at the truck at the bottom and the human beings standing there down there on the far right. And imagine how big, just imagine how big the fans are. So what do these fans do? These fans spin at extremely high speeds. And what happens is that they filter the carbon dioxide, which is present in air, and that filtered carbon dioxide, and then it's going to be transferred into different containers, and it is then there's going to be pressure applied on that gas, and that is when it's converted into its liquid form, and that is when it can be used in various ways. We're going to see what ways we can use. So industrial use of CO2. This is what I mentioned to you earlier. Yes, CO2 is not just a garbage. It's not just a waste. We can use carbon dioxide in many ways, which we're going to see right now. So McKinsey and Company, so these are the finance people, these are the finance company back in the United States. So they have estimated that by 2030, carbon dioxide-based products could be worth more than $800 billion. Imagine 800 billion to 1 trillion is how much the carbon dioxide-based products could be worth by 2030. And the use of CO2 for producing fuel, for enriching concrete, which we're going to see in the upcoming slides, and generating power alone could reduce the greenhouse gas emissions by 1 billion metric tons. Imagine, a ton is 1,000 kilograms. So imagine 1 billion tons, metric tons of carbon dioxide can be reduced in the air. Okay, so you're going to bring the numbers back to normal. So 0.004 will certainly come back to 0.04% carbon dioxide present in air. Will certainly come back to around 0.03% if this method is followed. But we're still taking the baby steps right now. We're still doing doing things in a smaller scale just to see whether they're working or not. Nothing has been done in a larger scale. That's something which I'm going to be talking about in the conclusion part of this presentation. And then the first method, industrial use of carbon dioxide, the first method in which carbon dioxide can be used is for enhanced oil recovery. So enhanced oil recovery. Check out this picture over here. Come on. Something is happening here. Okay, I'm sorry about that. So enhanced oil recovery. So you know what, the fossil fuels, the oils which are somewhere at the bottom. So what you would do is that you dig a pipeline on one side and dig another pipeline on the other side. And what you do is you inject CO2 through the other pipeline. So what CO2 does is that when you're injecting CO2 in the liquid form or in the gaseous form, what happens is that it develops a pressure underground. And what happens if it develops the pressure underground? It forces the oil from the other opening. It forces the oil upwards from the other opening. And this enhances the oil recovery. Okay, so likewise, this CO2 can be injected into greenhouses. You might have seen greenhouses. I'm pretty sure. I mean, I've seen greenhouses like where when in the universities where I studied and worked back in the United States. Every university has a greenhouse because every university has a biology department where they raise certain plants in controlled conditions. So CO2 generally gets injected into these greenhouses because these greenhouses have some special features. They are used for, as you look at the picture at on the bottom right, you see that their greenhouses are used for growing vegetables as well as flowers, and different kinds of plants which are hard to grow in a regular land, in regular climatic conditions. So greenhouses create specialized conditions. As a matter of fact, in Bangalore, there's a so-called Lal Bagh. I'm pretty sure you guys might have heard of Lal Bagh, which has a big botanical garden and all that stuff. And it does have a greenhouse where the plants are grown in controlled fashion. So what happens when CO2 is injected into these greenhouses? The plants will start producing a better yield. This is not, I'm not something that I'm just saying. This was experimentally proved that plants will start showing a better yield when more CO in the presence of more CO2, because that is what is required for their photosynthesis. The greenhouses do provide artificial sunlight and everything. So in that process, if they even provide artificial carbon dioxide, that is when the plants start producing a better yield. Likewise, carbon dioxide can even be used in concrete by converting gaseous carbon dioxide into solid mineral carbonates like calcium carbonate by a process called as calcium CO2 mineralization, which we have seen in the earlier slide, something similar to this one. So what exactly happens is cement is mixed with water, it produces calcium ions. Likewise, CO2 mixed with water produces carbonate ions, and calcium and carbonate mixed together to form the calcium carbonate, which is a solid limestone. Okay, so CO2 is also can be substituted for water in the curing process. Curing process. So what is curing process? You might have heard of curing the meats. So sometimes in the United States and other countries, I've seen in some of the European countries as well, they cure the meats. The meats are made to, they cut the meats into smaller chunks and they cure them, which means that they apply salt and other spices and they let them stay for 1 year or 2 years to get the required texture. So likewise, curing in case of cement is that you're making sure that the cement attains the original form, the form that you're looking for. So in that case, what you're going to do is you're going to take a big chamber and going to put all the cement things, whatever you made out of the cement, and then you pump in the carbon dioxide gas, and that is what is called as curing. And this results in much stronger concrete, which means the concrete which is formed as the end product is much stronger than the one which is formed by curing by using water. And by this process, you're even saving a lot of water. So this is for places where they have a shortage of water. And CO2 is even used in calcination of calcium carbonate. Calcination of calcium carbonate is it's a very common procedure which is used in cement factories. So calcination is like you take a calcium carbonate solid and then you heat up to extremely high temperatures, and that's when you see the formation of calcium oxide and the release of carbon dioxide. And the carbon dioxide which is released through the exhaust is collected and it is compressed and stored, and it is stored or used for various purposes. So okay, there are different plants, right? As of now, there are different plants to capture and sequester or reuse the evolved carbon dioxide in this process of calcination of calcium carbonate. So, and the fourth one is a cement, which there's the Novacem. So Novacem is a company which has come up with a particular kind of a unique cement. What it does is that it has the capability to absorb CO2 by itself. So as a matter of fact, 0.6 tons of carbon dioxide gets absorbed by 1 ton of cement, which is a great contribution. 1 ton of cement, if it can absorb zero point 0.6 tons of carbon dioxide, that's incredible. I mean, if we can use that kind of cement for building all the houses, then that's going to be amazing because we're going to be having a decreased concentration of carbon dioxide in air. And this is I got this information from a beautiful article from published in the Guardian. Guardian, I think it's a British website or British news agency. So the cement that eats carbon dioxide. That's the title of this particular article. It's a beautiful article. If you want, you can check it out. The cement that eats carbon dioxide. You can just Google it and say the cement that eats carbon dioxide, the Guardian, and boom, you'll get it. It's just a beautiful way of uh, making a cement which can absorb carbon dioxide that's present in air. And the second one, or the next one is the carbon dioxide scrubber. So what the hell is a scrubber? So we'll look at that scrubber thing in a moment. So it's used as the CO2 absorbers. These scrubbers are used as CO2 absorbers. Looks like I started having some questions already. How to absorb. Okay, we'll talk about all these things. Yeah, well, I have answers for all the questions that you're asking, but we're kind of running short of time, so I have a lot of slides to finish up, and so little time. So carbon dioxide scrubbers is used as CO2 absorbers, are used in the treatment of exhaust gases from industrial plants, exhaled air in life support systems, so exhaled air in life support systems. So so let's say you got sick, and whenever you put in an intensive care unit in a hospital, then they put you those masks which supply oxygen, but you might be wondering, where is the carbon dioxide going? So that is where they use these carbon dioxide scrubbers. So is the case in aircrafts as well as in submarines. Submarines will be, as you know, submarine, which means that they're going to be always underwater. So you might be wondering where is that all the carbon dioxide which they are exhaling out going. So there are certain things, certain materials which have the capability to act as absorbents. Okay, the first example of this carbon dioxide scrubber is the amine scrubber, and it is used in coal and gas-fired power plants. What exactly happens is that you start with carbon dioxide reacts with ethanol amine to form these two compounds. One of them is like the zwitter ions. One of them is positive charge. The other one is negative charge, and the reaction happens in cold conditions. And look at this arrow over here. The reaction happens in cold conditions. When the temperature shoots up, then the reaction follows the backward reaction. Okay, the reaction follows the backward path, and in the cooler conditions, it follows the forward path. Excuse me. So these are the most relevant solvent combinations like piperazine, potassium carbonate. So these are the various solvent combinations which can be used as amine scrubbers. And then we got the mineral scrubbers. So what exactly are these mineral scrubbers? Several minerals and mineral-like materials reversibly bind CO2. So they reversibly bind CO2, which means they absorb and they can even desorb as well. So most often these minerals are oxides or hydroxides. For example, you have sodium hydroxide, lithium hydroxide, which is what I'm going to be talking about on this slide. What they do is upon sodium hydroxide, as a matter of fact, even in my laboratory, so we have the so-called desiccators. So there are certain compounds which tend to be sensitive to carbon dioxide. And that is when we put a small amount of sodium hydroxide in a small beaker and put it into the desiccator. So what does this sodium hydroxide do is that it absorbs the carbon dioxide which is present in air, so that the compounds which you have put in the desiccator tend to be stable. Okay, so that's exactly what is happening here. So sodium hydroxide is reacting with carbon dioxide. Sodium hydroxide is reacting with carbon dioxide to produce sodium carbonate and water, and that sodium carbonate reacts with calcium hydroxide to produce sodium hydroxide and calcium carbonate. And this calcium carbonate goes through a process called as causticization, which is very common, ubiquitous, very common in paper and pulp industries. The calcium carbonate gets converted to calcium oxide, thereby releasing carbon dioxide, which can be trapped, and it can be compressed and reused for a different purpose. Likewise, lithium hydroxide absorbs carbon dioxide to form lithium carbonate and water. And yes, calcium carbonate, lithium carbonate, these are not water soluble. They sit that way for hundreds of years. They are extremely stable compounds. And the third one is the regenerative carbon dioxide removal, which is something which is used in space shuttles. The carbon dioxide removal assembly constitutes of primarily resin beds. So what they use in the space shuttles is that they use the so-called resin beds, which work on the adsorption principle. Absorption is different from adsorption. Absorption is a universal phenomenon. Adsorption is a surface phenomenon. So resin used in the system has the property to bind the carbon dioxide molecules, which dissolve, while dissolves the same if heated to a certain temperature. That is what called as adsorption and desorption. So it adsorbs the carbon dioxide, but if you want to reuse the resin, what you're going to do is you're going to heat it up to a certain temperature. That's when you get the resin back and the CO2 goes out. Okay, so this is what the model looks like in a space shuttle. So in a space shuttle, you generally use a hydrogen oxygen fuel cell. I can talk to you about this, but we don't really have enough time, and this is not relevant to the the existing talk. So we have this hydrogen oxygen fuel cell, which is what produces water and electricity. The water which is produced by the hydrogen, but by the fuel cell, the hydrogen oxygen fuel cell, can be used for the consumption can be used for consumption by the people, by the astronauts who are in the space shuttles. Okay, so the water which is present takes electricity and forms hydrogen and oxygen. The oxygen which is generated in this process is taken by the astronauts or the cabin crew. And the hydrogen which is generated, okay, and the cabin crew, what they do is they inhale oxygen and they exhale the carbon dioxide. So where does the carbon dioxide that's exhaled out goes? It goes to it gets to this carbon dioxide removal assembly, where it reacts with the hydrogen that is produced from water to form methane. Methane can be used as a fuel, or it can be just stored until the astronauts come back onto planet Earth. And in all these processes, look at the blue arrows. The blue arrows produce water, are the ones which saying that the port is produced. The water which is produced is recovered, and that water is what is consumed by the astronauts. Okay, and the fourth one is the activated charcoal. Air with high carbon dioxide content can be blown through beds of activated charcoal. So excuse me. So this is the two different kinds of charcoal. The charcoal on the left-hand side is the granulated charcoal, and the charcoal on the right-hand side is activated charcoal, which is extremely fine powder. If the powder is fine, what happens? The surface area of the particles is going to be more. If the surface area is going to be more, then they can absorb carbon dioxide to a greater extent. So once the bed is saturated with carbon dioxide, it must be regenerated by blowing low carbon dioxide air, such as ambient air, through the bed. Okay, so once the bed absorbs all the carbon dioxide, then you just blow air through it, and that's when all the carbon dioxide gets released, and you get your activated charcoal back, which can be reused again and again. And I found it beautiful. This is something which is an incredible thing which I found online: metal organic frameworks. Metal organic frameworks. Look at these beautiful lattice structures, the cubic lattice structures. So these are one of the most promising new technologies for carbon dioxide capture and sequestration via absorption. Metal organic framework could be specifically designed to act like a CO2 removal agent in post-combustion power plants. We're talking about post-combustions. After combustion is where you see the release of carbon dioxide. So that is where you put these metal organic frameworks, because they have the capability to check this out. So you see the metal organic framework over here, and look at the green arrow. On the arrow, you have the gases coming out through the post-combustion power plants, and the CO2 is the red one, and the H2 is the blue one. CO2 gets absorbed by the metal organic frameworks, and the hydrogen gets purified and it gets sent out, or it gets grabbed or done something else. Hydrogen can be used in multiple ways for running various reactions. Okay, so it can be used in the post-combustion power plants. In this scenario, the flue gas would pass through a bed packed with metal organic frameworks where CO2 would be stripped or would be trapped. After saturation is reached, the CO2 could be restored by doing a pressure or a temperature swing. So either if you increase the temperature, so on the right-hand side, so once the CO2 gets trapped in the metal organic framework, so either you can increase the temperature of it to release the CO2 out of the metal organic framework, or you can even subject it to extreme pressure conditions. That's when you can get the CO2 which is trapped in it out of the framework. I found this beautiful article on the American Chemical Society, carbon dioxide capture in metal organic frameworks, which talks beautifully about this very same procedure, about how to grab carbon dioxide, which is present in other gases as well as in air. And then I found another beautiful article, which is from Chemical Society Reviews, which says about carbon capture and conversion using metal organic frameworks based materials. Now, check this out. This is what the metal organic framework looks like. Oh, gosh. I got to escape. Okay, I'm sorry about that. So look at this metal organic framework. So what is happening? So look at the big arrow, the green arrow. The CO2 gets captured in the metal organic framework. So this entire big thing is the metal organic framework. So CO2 is getting captured in it and it is getting reduced. Reduction is happening in the same metal organic framework. Here you go, it says carbon capture and conversion. So you're converting the carbon dioxide to a carbonic acid. So are you converting it, you're reducing it. So you're capturing the carbon dioxide as well as you're converting that captured carbon dioxide into a product which is more beneficial to mankind. Okay, and next is the basalt storage. So I found a lovely paper on Elsevier, which is a CO2 storage potential of basalt rocks offshore Iceland. So this is a paper which was published by a bunch of scientists from the University of Iceland in Iceland. So what exactly they did is they injected CO2 into the basalt formations, which provides significant benefits, including permanent storage by mineralization and large storage volumes. Look at this. So water and storage are pumped in at the same time into the basalt rocks, which are underneath the sea. So this is what happens. The carbonate minerals, they get stored. So check this out, basalt rock. You might be wondering what basalt rock is. I'm going to tell you in the upcoming slide what exactly basalt rock is. Basalt rock is a volcanic rock. Okay, so that reacts with CO2 to form the carbonate, which is going to be sitting underneath the Earth's surface, and it is going to be sitting there for millions and millions of years. And that is the best possible way to one of the best possible ways to store carbon dioxide. And the largest geological storage potential lies offshore, and in the case of basalt, along with mid-oceanic ridges where CO2 could be stored as carbonate minerals for thousands and thousands of years. So now you might be wondering what exactly basalt is. Basalt is the mafic extrusive rock. In simple words, it's a volcanic rock. It's a rock which is formed by the lava, whatever the magma, whatever comes out of the lava over the years, about thousands of years. It forms basalt, which is a hard rock, and it's not really hard, it's very soft. So because of its relatively low silica, it has about 90% of comprises more than 90% of all volcanic rocks. Because of the relatively low silica content, basalt lava has a comparatively low viscosity and forms thin flows that can travel through long distance cells. Okay, so this is what the basalt rock looks like, and this is actually it's a life size. You can say that it's about 6 feet tall. I've seen it in person. It is at the Victoria and Albert Museum in London, and this is the Lord Shiva, which came from southern India. It's one of the temples of southern India. I think it's in the Victoria and Albert Museum in London. It is made up of basalt, which is a volcanic rock. Oh, you're frozen. Are you? No. Okay. So the next way of chemical method is acid neutralization. So addition of crushed limestone to oceans enhances the absorption of carbon dioxide. So yes, limestone is calcium oxide. You add calcium oxide and it absorbs calcium carbonate, absorbs carbon dioxide, dissolve when atmospheric carbon dioxide dissolves in water, it reacts with carbonate ions in the surface water to form the bicarbonate ions. Okay, and apart from that, you can even add sodium hydroxide to oceans. So what exactly is sodium hydroxide doing? Sodium hydroxide, it reacts with the acids which are produced in the oceans, which are released into the oceans. Here you go, sodium hydroxide reacts with the acid. As a matter of fact, CO2, though it doesn't have any H plus ions, it doesn't produce any H plus ions, CO2 is acidic in nature. So sodium hydroxide reacts with carbon dioxide, which is present in water, thereby converting it into sodium carbonate and water. And so that the pH of the ocean gets restored to 8.1. Yes, the pH of the oceans is slightly alkaline in nature. Okay, and that's it. We're done with the chemical methods. So let's jump into the biological methods, and we have like 10 minutes to go. Hopefully, I'm going to be provided with some extra time so I can explain to you a little more in detail. So biological methods, biosequestration, it's called as a biological method. Sequestration by biological method is always called as biosequestration, which affects the global carbon cycle. So major climatic functions, fluctuations like the Azola effect. What is Azola effect? Azola effect is something which came into existence about 49 million years ago. And that is what created the climate. So 49 years ago, look at this, on the Earth, planets all look like a big one. Okay, and that is this, they had seen this Azola effect at that time. And what happened is Azola is the fern, this green fern that you see over here at the bottom left. So this is what this is just an example of what it used to look like, what the oceans used to look like. The ferns used to cover the top of the surface of the ocean. And what happened is that this fern used to sink to the bottom of the oceans, thereby taking all the carbon to the ocean floor. Okay, it's, that's that's called as biosequestration. And the first example, the first way of doing biosequestration is by using peat bog. A bog is a wetland that accumulates peat, which is a deposit of dead plant material, which often are mosses. Mosses are like the bryophytes. So you have pteridophytes, thallophytes, bryophytes, and the pteridophytes. The bryophytes are the ones which are considered as mosses. It is one of the four main types of wetlands. Other names for bogs include the mosses, the quagmires. You might have seen quagmires in the movies. The hero and the heroine, they go in the movie into a forest, and the hero jumps into, he falls into a sand, a loose sand kind of a thing. So that is called as a quagmire. Okay, so and the heroine pulls him out, or maybe not, or maybe she goes and jumps along with him into the thingy. But so that's called as a quagmire or mosses or mires. So peat blogs act as sink for carbon due to the accumulation of partially decayed biomass that would otherwise continue to decay completely. And then you have forestry. Forestry, you might have heard of forestry. You know what, everyone knows what forestry is. The forestry is the reforestation, and reforestation is replantation of trees on marginal crop and pasture lands to incorporate carbon from atmospheric carbon dioxide into the biomass. The wood from them must itself be sequestered in the form of biochar. So what exactly is biochar? We're going to come across this biochar in the upcoming slides again. Biochar is the obtained by pyrolysis of biomass. Biomass is plants, trees, everything. Pyrolysis, pyro, which means fire. Lysis is breakdown or subjecting to fire. So when you burn something in fire, that's when you end up getting with carbon storage, landfill, or it can be used even in construction. Yes, I've seen this biochar which is being used in construction as well. As a matter of fact, we're going to talk about this in upcoming slides a little more in detail if we have enough time. So wetland restoration, wetlands have the capability to store a lot of carbon dioxide. It is an important carbon sink. It is an important carbon sink. It's an important carbon storehouse. 14.5% of the world's soil carbon is found in wetlands, while only 6% of the world's land is composed of wetlands. So wetlands, look at this picture on the right-hand side, on the left-hand side, this is what a wetland looks like. On the right-hand side, check this out. The plants, they absorb a lot of oxygen. the plants, they absorb all the oxygen. Is everything okay? Okay. So the plants, they absorb oxygen, and that is it gets absorbed by the wetland. So the plants, the sand which is present in the water, they absorb all the. I'm going to make it full screen. Just 5 minutes to go. But and agriculture, you probably might have heard of agriculture. Agriculture is one of the ways in which you can absorb carbon dioxide. Soils are estimated to contain about 8,500 gigatons of organic carbon, which is about 10 times the amount in the atmosphere. So if you make the soil more and more rich in carbon, that itself would reduce the carbon dioxide concentrations in the atmosphere. And then you have carbon farming, which is the process of changing agricultural practices or land use to increase the amount of carbon stored in the soil and vegetation. You probably might have known about this one, so I'm just going to go into skip to the next slide, which is soil. Soil carbon sequestration is the process in which carbon dioxide is removed from the atmosphere and stored in the soil carbon pool. Check this out, the diagram on the picture on the right-hand side. So the atmospheric carbon is taken over by the plants, and the plants, upon decomposition, form humus, which is what is going to be remaining in the soil. Humus is a very good source of the decomposed part, and it's a very good source of carbon, and it's even going to be useful for soil, for fauna and the microbes for their growth. And iron fertilization, this is extremely unique. So phytoplanktons, as a matter of fact, ships in the past, I would say in the early 1900s, they deposited tons and tons of ferrosulfate into one of the seas in Europe. So phytoplankton, so what happened is that the bacteria, the algae, the phytoplanktons. In this case, you see the phytoplankton. This is the phytoplankton which is present in those waters. It has the capability to absorb iron salts which are present in water, and thereby absorbing carbon dioxide from air. So phytoplankton is photosynthetic, needs sunlight and nutrients to grow, taking up the carbon dioxide in the process and producing oxygen as a byproduct. The phytoplankton then dies, falls to the bottom of the ocean, and takes that sequestered carbon dioxide with it. So all what the carbon, whatever it absorbs, it goes down to the ocean surface, and that's where it survives for centuries, for millions of years. Okay, so one of the major nutrients of phytoplanktons needs to grow is iron, and if that iron is supplied, what happens is that the bacteria, which are the phytoplanktons which are present, not the bacteria, the phytoplanktons which are present in water, they absorb carbon dioxide which are present in air, and they once they die, they get transferred to the bottom of the ocean. So this is a beautiful way of iron fertilization. Likewise, you have another fertilization. So this is an example of iron fertilized area in the Barents Sea. Barents Sea is in between Russia and Greenland, right above Europe. And these are the algae which grew here, and these are the ones which can consume the iron, and they can absorb carbon dioxide from air, and they can, once they die, they settle down at the bottom of the ocean. Okay, so just like iron fertilization, we even have the urea fertilization, which is science, which is the removal of the carbon dioxide by using urea instead of iron salts. Okay, so but there are always negative things going on. So someone wants to do something, there's always someone pulling them back. So there's a beautiful article which is published in one of the Elsevier journals, which is Marine Pollution Bulletin. It says that ocean urea fertilization for carbon credits poses high ecological risks, which clearly means that it is not a good idea to dump urea into the oceans. And as a matter of fact, in order to synthesize urea, you need to burn fossil fuels. Yes, you need to burn fossil fuels in order to synthesize urea. But again, you're putting urea into the ocean, and it's going to be absorbing carbon dioxide. So what's the point in burning fossil fuels and making urea when urea itself is not made that in that easy way? So that is there. And then you can even start growing seaweed. Seaweed, like land plants, use photosynthesis to turn carbon dioxide into a seaweed biomass. So once they die, they sink to the bottom, and that's where they store all the carbon. And then there's this beautiful. Well, I thought I'm done with my presentation, but then I came across this beautiful article about carbon capture microbes. So there was this one company in Australia which came up with this beautiful method. What they did is they took a few seeds and they hand painted the seeds with microbes, so certain microbes. And what they have found is that the yield of those of those plants is pretty high in comparison to the plants which are grown in regular normal conditions. So what they're saying is that these bacteria and fungi, they have the capability to absorb carbon dioxide which is present in air, thereby helping the plant to grow, to give a better yield. So this is an amazing process, and if this really is going to be a successful idea, then these bacteria can absorb most of the billions and billions of tons of carbon dioxide from air, which is just the greatest thing. So this is the article which I found. Seeds coated in microbes give plants superpower carbon capture abilities. And the next comes the physical methods, the various physical methods. So the first physical method is the bioenergy. It's the process of extracting bioenergy from biomass and capturing and storing the carbon, thereby removing it from the atmosphere. Okay, so we might be wondering what biomass is. Biomass is something which is obtained from the dead animals and the plants. So all these, they combine together, they form the biomass, and that upon burning gives bioenergy. Or you can even bury the biomass. Like you see the petrol and the diesel and the coal which we're using every day, that comes from the fossil fuels. So how did the fossil fuels form? At one point, the trees and the plants and the trees and animals, they were embedded deep underneath the earth's surface, and that is when they end up forming the fossil fuels over millions of years. So we can do that manually. So it mimics the natural process of creating the fossil fuels. And burying the biochar. Biochar is charcoal created by pyrolysis of biomass. So you are just burning the biomass, and that produces biochar. And this resulting material is added to the land, and that creates the so-called terra preta. This is what the soil looks like. Terra preta, the advantages: it's extremely fertile, increase the pH of the acidic soils. Because of soils are acidic in nature, the pH becomes more neutral or more of a basic kind. It helps to retain nutrients such as ammonium, calcium, and other stuff. The porosity helps them to trap moisture and increase the water retention of soils in dry region. Okay, so the next one is the storage of CO2 in oceans. So oceans are the best places to store CO2. So what can be done? Injecting CO2 at depths of 1,000 meters below the sea levels. Check this out. You can maybe this picture explains to you everything. So if you can even inject the supercritical carbon dioxide into water at around 3,000 meters, because the pressure of water is going to be pretty high. At that point, the carbon dioxide is going to be still in its liquid form, and it's going to be sitting there forever. Okay, so consequences, there are certain consequences always affecting it affects the deep sea life. So what of the animals which are living here will be struggling to survive because they can't take more of carbon dioxide, and it decreases the pH of seawater. As I mentioned to you, CO2 is acidic in nature. When it combines with water, it forms carbonic acid. So that acid decreases the pH of seawater. And here is a graph which explains to the solubility of carbon dioxide in water. And geological sequestration, one of the most important ways of sequestration is geological sequestration. Yes, even this one has some negative feedback. So storage of CO2 underground in depleted oil and gas reservoirs, saline formations. Check this out. The picture explains to you everything. How you can store CO2 in its supercritical form underground in various gas reservoirs or saline formations, or deep unmined coal beds. So the density of supercritical carbon dioxide is about 600 to 800 kilograms per meter cube. It's pretty heavy. That's the reason why it would sit at the bottom. It wouldn't even think of escaping out. So you can just store this CO2 in a supercritical form underground, so that it can be safe. And important parameters in determining a good life for carbon storage are the rock porosity. So you might be wondering, what can, well, you can't really store carbon dioxide wherever you want. The rock porosity, rock permeability, absence of faults, and geometry of the rock layers, they matter a lot. The medium in which CO2 is to be stored ideally has a high porosity and permeability, such as a sandstone or limestone, the pictures of which you have at the bottom of the slide. While trapped in a rock formation, CO2 can be in a supercritical fluid phase or dissolved in groundwater. Okay, so these are the various numbers. The worldwide storage capacity in oil and gas reservoirs is very small, but when it comes to deep saline formations, they have the largest capacity to hold carbon dioxide, which is about 1,000 to 10,000 gigatons of carbon dioxide. Now, we've come to the conclusions part of the presentation. So from the conclusions, I would get started by saying that carbon sequestration is a broad and important subject. It is essential in the effort to circumvent the effects of climate change. Carbon capture and storage is one of the most important and effective and discussed methods of solving this issue. So you got to capture it and store it. So in order to reverse the effects of climate change, carbon capture and storage must be coupled with methods of generating cleaner energy. Yes, you got to think of not just capturing and storing it, but you got to think of ways to generate cleaner energy so that there is no carbon being released into the atmosphere. Okay, so cleaner methods of farming, reforestation, afforestation are effective methods of restoring natural methods of sequestration that existed before we human beings tampered with the environment. So we got to indulge ourselves in cleaner methods of farming, reforestation, and all these activities. And concerns exist over injecting. There are a lot of concerns. As a matter of fact, there's environmental activists. So if someone wants to do something, the first people who come and raise their hand say like, oh, the environmental activists, they'll be like, okay, you know, you can't do this. You're ruining the environment. No, you can't do this. You're ruining you're killing all the animals. That's what they come up with. So concerns exist over injecting supercritical carbon dioxide into oceans as well as into the soils. Carbon sequestration is still in the nascent stages as it has not been commercialized yet, but many experiments have been carried out in a smaller scale. So the plans are on to do the same in a larger scale. And this is a slide which but we don't really have enough time, but this is me in front of my institution where I graduated back in the United States. This is my research lab right now. We're just still under construction. And I'm looking forward to have research scholars working on my research projects. We're very happy to have PhD scholars working on these projects. And here's my contact information. You can find me on ResearchGate or Google Scholar. And now it's time for questions.
So good afternoon, sir. This is Raghuvanshi.
Hi, how are you?
I'm fine, sir. Sir, a few questions has been asked by the participants in the Q&A box, beside chat box. You can look at those questions and you can answer them.
I am. Okay. Okay. What is the reaction condition of carbon dioxide with oxides or silicates? What are the reaction conditions? They go at slightly, are these natural processes? No, they are not natural processes. I wish they are natural processes, but you need to supply some heat for the reactions to happen. The first step of sequestration is capturing. How capturing can be done on a larger scale? I think I've already answered this to you. You can use special fans which do have the capability to filter carbon dioxide from air. And that can be used for storage or compressed and stored or reused. Okay, is there any possibility to reduce carbon by recycling process? Recycling of what? Is there any possibility to reduce carbon by absolutely yes. Come on, recycling is one of the best options which we always think of. It's always good to recycle stuff rather than going for something new. Yeah, and the next question, how to absorb CO2 in gaseous form from roadside to store in a cylinder? Is there any instrument? I mean, as I mentioned to you in one of the slides, there are certain resins which have the capability, and likewise, even the MOFs, the organic frameworks, which you can use. And yes, they have the capability to absorb carbon dioxide from roadside. Absolutely, yes. You can put it in your house. You can put it in a roadside, anywhere. It can be done. And does CO2 have any toxicity apart from being a greenhouse gas? It does not have any toxicity electricity. As a matter of fact, I don't know whether you know or not, in medical industry, CO2 is used as a respiratory stimulant. Okay, if someone is having a difficulty in breathing, they pump in some CO2. So see what CO2 does is it helps the person to breathe better. So it's called as a respiratory stimulant. So I don't think it is toxic. Okay. Can you compare the greenhouse potential of CO2 with methane gas? Greenhouse potential of CO2. Well, methane catches fire right away. CO2 does not. Maybe that can be one comparison that I can come up with as of now. I can look it up and get back to you later on. I guess there must be a limited concentration of CO2 to be used for scrubbing reaction, either with mono or diethanol amine, etc. Can it be appreciable for CO2 emitted from exhaust? Well, there are different kinds of scrubbers which are meant for different kinds of purposes. So maybe, yes, you can use this amine scrubber for, ow, something got into my ear, I'm sorry. So maybe you can use the same amine scrubber, maybe a thicker version of it, which has the capability to absorb more of the carbon dioxide, which is produced, sent out through the exhaust. So what is the reason behind the reason of absorption? Water has, that's a beautiful question, I gotta tell you. That's the reason why I've shown you one graph. A graph in one of my slides shows the extent to which I knew that I'm going to get this question. So I've incorporated this graph in one of my slides, which tells you the solubility of CO2 in water, which is higher than what it is in air. Get it? So what about so what is the reason behind to absorb CO2 by ocean? Ocean water absorbs CO2 to a greater extent. Of course, if the temperature goes up, solubility of the gas decreases. If the temperature goes down, solubility increases, which is regular physics. I'm pretty sure you guys know that. So what about the medical wastage deposition in soil or somewhere? I don't know what kind of a question that is. I don't know what exactly you're looking for, Mr. Chandrasekharan. In that case, the CO2 level in atmosphere, that increase the CO2 level in the atmosphere. Medical wastage deposition. Medical wastage deposition. You're talking about like syringes and needles. If you deposit them, they're not. I mean, that's plastic. You know, syringes and needles they're not biodegradable. So they just sit as such for years. They don't degrade. You know, so can we measure contents of CO2 released from mobiles and laptops? I don't know. I don't have an answer for it. Can we measure the contents of CO2 released from? Maybe there are ways to do it. So maybe if you put your laptop in a sealed chamber, then probably if you attach a gauge, a pressure gauge or something of that kind to it, and then you can probably figure out how much of CO2 is being absorbed. As a matter of fact, you can do it in a different way. So as I said to you, I mean, in my chemistry lab, what we do is we put potassium hydroxide, sodium hydroxide in the desiccators, and later on, what we see is if the potassium hydroxide is become white, like potassium carbonate, then we discard it. So what you can probably do is you can start with potassium hydroxide. You can take potassium hydroxide in the desiccator and you can put your laptop in there and leave it over there for a few days and then see to what extent the potassium hydroxide got converted to potassium carbonate. And based on that, you can do some analysis and find out how much of carbon dioxide is being released from your mobiles as well as your laptop. I hope that the answers sound appropriate.
Yeah. I think no more questions, sir.
Right. Yeah.
Okay. Yeah. Thank you, sir. Thank you very much.
Sure. I hope everyone did learn something out of it about carbon sequestration. I mean, it is, as of now, it is the most important thing in the world because of the increasing levels of carbon dioxide. Carbon sequestration is pivotal importance in the society. We all have to do something either to reduce the emissions or to store the carbon dioxide which is already emitted by other people. I'm glad that you guys have absorbed some of the knowledge, not the carbon dioxide, but some of the knowledge.
Yes, sir. Yes, sir. Thank you, sir. Thank you very much.
Sure. Yeah.
That was a nice presentation on carbon sequestration. I hope this could be a great source of valuable information for the participants who are doing their active research in this field. The presentation also highlights the increase in concentration of CO2 in the atmosphere, which is related to environment. That was a good illustrative display by Vikram Baswa, sir. Thank you, sir. Thank you for being with us and for your valuable time. I thank all the participants for their active participation for the whole day. So I request all the participants who can join their session for the third day of Atal FTP. Thank you all. Thank you, sir. Thank you very much.
Thank you. I thank the mechanical department for giving me the opportunity to be a part of this session. Thank you.
Thank you, sir. Thank you.
Yeah.
Okay, sir.
Thank you, everyone. Bye-bye.
Okay, sir. Bye, sir.